So as usual, welcome everybody to this official IAU G2 online conference series. This is about massive stars, and we are already in the 9th seminar. So this is very good. It's almost 1 year since we started, and we already have the pool of potential speakers for the next year. So I think these are very good news, and you will have more information soon. So today we have Eoin Farrell from University of Geneva. But before introducing him, I wanted to say a few things as announcements. So the first thing is thank you everybody who answered my questionnaire about this conference series. So remember that anytime you are open to send me suggestions for improvements or potential speakers that you consider could be of interest. Obviously, for this, I need your help because I don't know all the community, and maybe there is some specific topic that have not been covered yet, and many people is interested. So please send me a mail if whenever you want. Then the second thing is remember that tomorrow is the deadline for nominations for members of the IAU organizing committees. We already have several very good candidates, but if you are still considering this option, please go ahead, because the more candidates we have, the better. And then finally, the last thing I want to tell you is about these online lectures. This is an initiative that Joachim Puls proposed as the committee a few months ago, and we decided to go ahead. So this is now starting. In 1-2 weeks, we'll have the first meeting of the committee to start like brainstorming of how things are going to be done. So in two kind of things I wanted to tell you. The first thing is that if you didn't know, but you think you will want to be part of this organizing committee, who will be defining the structure of the lectures and the courses and everything, please send Joe Puls or myself a mail, and then you will be also included. And also to tell you that obviously, again, you will have more news about this initiative, but obviously we will need your help for kind of supervision of some of the lectures. So yeah, you will have more info about all this, but just for you to know that this is coming. Okay, so now we go to the introductions. It's a real pleasure for me to introduce Eoin Farrell from University of Geneva. He did his PhD in Trinity College of Dublin under the supervision of Joseph Grove, and he finished in 2022. And after that, he moved to Geneva Observatory as a postdoc, working in the group of Jos Maynard of Massive Star Evolution, and he has been there for the last 18 months. He has been mainly working on massive stars, and by checking his ADS this morning, I found that even his early career, he's done he has covered already many different branches, always in the framework of the study of massive stars. So for example, he's been interested in the connection between the stellar evolutionary model prediction and the observations, but also going to studies of magnetic fields in navy stars, the connection between gravitational wave events and black hole mergers, and also the final stages of massive stars and the connection with the polar supernova. But also he has been studying these supergiants and how binary evolution is helping us to understand what is the evolutionary status of these interesting objects. So it's already quite broad number of topics he covered. Obviously, he's not going to talk about all this today. He has decided a more specific topic. So yeah, I'm very happy to give you the floor, Eoin, whenever you want.
Great, thank you very much. So hello everyone, and thanks for coming to the seminar today. And I'd like to thank the organizers for the opportunity to speak with you. As Sergio said, I'm a postdoc at the University of Geneva, where I'm working on massive stars. And today I'd like to present the results of some numerical experiments on post-main sequence massive stars, and specifically trying to answer the question, what fundamental components of the stellar structure set the effective temperature of a post-main sequence massive star? In other words, what makes them blue or red? So as an outline to the talk, I'll begin by with a brief introduction and a motivation for the results that I'll present today. I'll then discuss the two main methods that I use, the standard numerical stellar evolution models and a modeling technique based on static stellar structure models that we developed called Snapshot. I've divided my results into 3 key points. Number 1, I'll discuss the results of a numerical experiment that demonstrates that small changes in the stellar interior can sometimes result in very large changes in the surface properties. Number 2, I'll discuss the key properties that set the luminosity and temperature of post-main sequence massive stars. And number 3, I'll discuss the consequences for some of these results in the context of interpreting observations of red supergiants and strip stars. And I'll end with some conclusions. So massive stars are clearly important to our overall understanding of the universe, and they're responsible for the generation of many of the chemical elements. Feedback from massive stars in the form of these elements, ionizing radiation and kinetic energy, drives the evolution of galaxies. They produce a wide variety of stellar types, for instance, blue supergiants that can be used for distance measurement, red supergiants, which are the progenitors of type 2p supernovae. A significant number of massive stars exist in binary systems, which are responsible for a wide range of astrophysical phenomena. Massive stars die in core collapse supernovae, which can leave behind neutron stars and black holes. And these remnants can merge in binary systems, emitting detectable gravitational waves. So today I'm going to discuss the key properties that set the luminosity and effective temperature of post-main sequence massive stars. And apart from being interesting to understand on its own, this is relevant for a range of other topics because the impact of stars on their surroundings and the rest of the universe through the emission of photons, the release of mechanical energy by winds, and release of chemical elements are, of course, all regulated by the evolution of L and TF. In addition, the evolution of L and TF affect the timing and outcome of binary interaction and the structure and binding energy of the envelope in the context of transients. So because our work aims to isolate the key features of the internal abundance profiles that set the luminosity and temperature, I first wanted to briefly mention some of the well-studied physical processes that affect the evolution of massive stars. So if mass loss is significant enough, it can drive a star to contract and evolve to the blue region of the HR diagram. Convective mixing impacts evolution in lots of ways, and it can drive the star to the red or the blue, depending on the location and extent of the mixing within the star. One of the primary impacts is to modify the convective core mass during hydrogen burning and the abundance profile outside the convective core. Interaction with a binary companion greatly complicates the possible evolutionary pathways that stars can follow through processes such as mergers and common envelope evolution. And depending on its nature and outcome, binary interaction can have a wide variety of effects on the surface properties. Stellar rotation is also important. And in general, moderate rotation favors evolution to higher luminosity and lower effective temperature during both the main sequence and post-main sequence, but fast rotation can produce evolution towards higher TF. And this is not meant to be an exhaustive list, rather just some examples. And despite the fact that these processes are well studied and reasonably well understood, it's still not always obvious what drives a star to evolve to the blue or the red in the HR diagram beyond describing what happens in stellar evolution models. And this is one of the key motivations for the investigations that I'll present today. including using static models as a complementary technique to evolutionary models. So there are several different methods and codes used to model stellar evolution. So I've used MESA in this work, but of course this can be done with other codes. And I thought I would just briefly remind you of some of the assumptions that go into these evolutionary codes. So similar to other codes, MESA models the evolution of stars in 1D and accounts for a range of physical effects. But at its core, it solves these following equations of stellar structure. So this is the usual equation for hydrostatic equilibrium, the equation for mass continuity, the equation for energy conservation, the equation for energy transport, and finally, the changes in the abundances for each isotope due to nuclear reactions. And in addition to these equations, a range of microphysical inputs are required, including an equation of state, capacity tables, and nuclear reaction network. And finally, stars are quite complicated objects with many different physical processes that affect their evolution, and some of which I just discussed. And these processes must be implemented or approximated or parameterized in some way in 1D evolutionary models, including mass loss, convection, rotational mixing, magnetic fields, and binary interaction. And it's really the implementation of these processes that account for most of the uncertainty in models of massive star evolution. So here's an example of a simple evolution of a single 16 solar mass star at solar metallicity in the HR diagram. So we have the hydrogen burning phase over here on the left. The dotted line represents the rapid expansion phase between hydrogen burning and helium burning. And the solid line over here represents helium burning phase during which the star evolves down from 0.2 and then back up to 0.3 at core helium exhaustion. So that's the typical output from a stellar evolution model. And this brings us to our approach using static stellar structure models, which we call snapshot models. To motivate the snapshot method, we'll just go back to this evolutionary model we just looked at and consider why the star follows this track exactly. What fundamentally causes the evolution up, down, and left and right in the Hertz-Malonza diagram? So while some of these answers are well known, especially for the main sequence, it's not always clear what the simplest explanation is. And if you look in the literature, you can find a range of different explanations for the same phenomenon sometimes. At lower metallicity, the star can evolve quite differently. So here's an example at SMC metallicity. And while we may understand that there's opacity effects here, we can also wonder exactly why this model follows a different evolution. And another way of framing the same question is what fundamentally makes the star blue or red here during the Boson sequence? This question is, it does have consequences for how we interpret an observation of a red or blue supergiant in terms of the internal stellar structure. So it's well known that stars evolve due to changes in their internal chemical composition, ultimately driven by nuclear fusion reactions. And in addition to nuclear reactions, their interiors are affected by many other physical processes, convection, rotation, etc., all of which have been studied in detail. Because these processes modify the abundance profiles in multiple ways simultaneously, it can sometimes be challenging to determine which parts of the chemical abundance profiles are primarily setting the observable surface properties, at least using stellar evolution models. So the usual approach to stellar modeling is to investigate the impact of different physical processes on the model outputs. And this has been highly successful for understanding the physics of stellar interiors, but it doesn't allow a straightforward systematic way to connect the internal and surface properties, and therefore an easy way to answer the questions that we posed on the previous slide. So for this reason, we developed this new technique that we call snapshot models. And our approach involves modifying one part of the internal chemical profile at a time and to test its impact on the surface properties. So how do we compute these models? Well, we want a way to solve the stellar structure equations for any arbitrary chemical abundance profile. And the easiest way to do this is to obtain a starting solution with a similar chemical abundance profile to what we want, and then modify the abundance profile and let the code find the new solution. So to do this, we first compute a normal stellar evolution model for the required mass, metallicity, and evolve to the desired evolutionary stage. The second step is to take a snapshot from this evolutionary model and modify the internal chemical profiles in the desired way. We then allow this modified profiles to relax to a thermal equilibrium. And the key advantage of this method is that we can repeat these steps 1, 2, 3 in a systematic way to build up a grid of models in which only one component of the profile changes at a time. So let's have a look at an example of one of these snapshot models. So we'll just remind ourselves of what the internal helium abundance profile of a post-main sequence massive star looks like. So this is a 15 solar mass star at SMC metallicity in the middle of core helium burning. We can divide the star into 3 main parts: the helium burning core, the hydrogen burning shell, and the envelope. So the model is located here in the HR diagram and will appear as a blue supergiant. Now we may wonder which properties of this internal abundance profile actually sets these surface properties. For instance, if the abundance profile instead looked like this, so the dotted line is the original and the solid line is the new one, perhaps corresponding to different rotational mixing, how would the position in the HR diagram change? And how do we answer this question? So as we discussed earlier, this will be difficult to investigate within evolutionary models because these abundance profiles are constantly being modified by a range of different processes simultaneously. However, we can use these snapshot models to do this. And if we compute the stellar structure that corresponds to this new abundance profile, we find that the surface properties of this new model appear over here in the HR diagram. So this will appear as a red supergiant with a radius more than 10 times larger than the original blue supergiant. So this snapshot approach allows us to extend this simple test by repeatedly, systematically changing the internal abundance profile, like all these models in the dotted lines, and find how the surface properties change, these points colored in white on the right-hand side. So one may wonder, why does the helium abundance profile have the effect that it does on the surface properties? Why is it the case that as you add more helium to the shell here, the star has a larger radius? And we'll come to that question in a couple of slides. So moving on to the results, the first key point I'd like to emphasize today is that very small changes in the internal abundance profiles can sometimes cause quite large changes in the surface properties. So as an example, here is a numerical experiment that follows in detail what happens to a stellar model when we modify the helium abundance profile by a small amount. So we begin with a 15 solar mass blue supergiant in the middle of core helium burning, similar to the model we just saw. And we see the internal helium profile. It's plotted up in the upper left. And the location of the star in the HR diagram is plotted in the lower right. So to help understand the cause and effect in a simple way, I've plotted 2 quantities in the upper right-hand plot. The first is the internal luminosity profile generated by nuclear reactions, plotted in dark blue and labeled L and nuke. And the second is the actual luminosity profile set by hydrostatic equilibrium, plotted in light blue and labeled L hydro for hydrostatic. So the key thing to remember about this panel is that if L nuke increases, this will favor an expansion of the star. On the other hand, if L hydro increases, this will favor a contraction of the star. And if L nuke is equal to L hydro, the star is at thermal equilibrium and it won't expand or contract. So in this case, the star is beginning at thermal equilibrium. These relationships follow from conservation of energy. So let's modify the helium abundance profile, and we'll follow the numerical experiment step by step. So here's the new profile in black in the upper left. And in the bottom right, we see that initially the luminosity and temperature are the same, as the changes have not yet propagated to the surface. In the bottom left panel, we plotted the ratio of the density, temperature, and nuclear burning profiles with respect to the original model. So when we increase the helium content in the hydrogen shell, this increases the molecular weight, which increases the temperature and density, which increases the nuclear burning luminosity in blue, and therefore, which increases the L-nuc. And as we said before, this will favor an expansion. So the star is now out of thermal equilibrium, and I'll play a short movie which follows what happens as the star relaxes back to equilibrium. So we see the star expand across in the HR diagram and become a red supergiant. As expected, the increase in the nuclear and in the value of L-nuc compared to L-hydro favors an expansion, and the star continues to expand until it reaches thermal equilibrium. So I'll just play that again, just to have another look. We see the radius changing significantly and finally reaching equilibrium. So a relatively small change in the helium abundance profile can, in this case, result in quite a significant variation in the surface properties. So obviously this is not always the case, but this is the point of this experiment, is to demonstrate that this can sometimes be the case. So this has implications for both interpreting the outputs of stellar evolution models, which can be quite sensitive to the internal abundance profiles, and observations of blue and red supergiants, which could, in principle, sometimes correspond to very similar internal structures. So the second result that I'd like to emphasize are the key properties that set the effective temperature of post-main sequence massive stars, which I'll now present 5 examples of. So first, this is the isolated effect of the central helium abundance. So I'd like to draw your attention to the abundance profiles of hydrogen and helium on the left-hand side. We have 3 static 16 solar mass models with the same abundance profiles in the outer envelope, and with different core helium abundances. On the right-hand side, we have the positions of each of these models in their HR diagram. So we can see that the 2 models with central helium abundances of 0.92 and 0.52 appear as blue supergiants, while the model with a central helium abundance of 0.07 is a red supergiant. And in fact, you can notice that there is a slight non-monotonic dependence of the effective temperature on the central helium abundance. This is due to 2 competing effects: the effect of the mean molecular weight in the core and the effect of the reduced fuel supply as the star evolves through helium burning. So initially, the effect of the mean molecular weight dominates, favoring expansion in the core radius and a corresponding decrease in the total stellar radius. However, for central helium abundance less than 0.5, so down here, the impact of the fuel supply in the core dominates, which favors a contraction of the core radius, and which corresponds to an increase in the total stellar radius. So this numerical experiment tells us that, all else being equal, models of massive stars will tend to evolve to the red towards the end of core helium burning. Of course, in a stellar evolution model, all else is never equal, and there are often other factors that one should take into account. So second, I'll just briefly remind you of the example we already looked at. So the helium content in the hydrogen shell affects the surface properties. So a larger amount of helium in the hydrogen shell favors a red star, whereas a smaller amount of helium in the hydrogen shell favors a blue star. And actually, just to point out, the dashed line in the plot here indicates the presence of a region in which no static structure model exists at thermal equilibrium. So third, we have the core mass ratio, which is defined as the mass of the helium core divided by the total mass. So a core mass ratio close to 1 corresponds to a helium core with little to no envelope on top. And such a star may result from interaction with a binary companion in which the envelope is stripped. For reference, a typical single 16 solar mass model may have a core mass ratio in the range of 0.3 to 0.5. And even lower core mass ratios, that is higher envelope masses, may result from binary interaction involving a merger or a mass gainer. So the figure on the right here shows the position in the HR diagram for a sequence of models with the same core mass and different envelope masses. And we see that there's a non-monotonic dependence of the effective temperature that's the result of two competing factors. So moving from a core mass ratio from this blue point of 0.82 to the red point of 0.55, we see a decrease in the effective temperature, which is due to the increased hydrogen opacity as a result of the larger envelope mass. Moving to even higher envelope masses, the actual impact of the mass of the envelope on the hydrostatic structure begins to dominate, and the increased mass favors a smaller radius and a higher effective temperature, which is what we see in the figure. Again, this dashed line represents an instability region in which no model exists at thermal equilibrium. So fourth, we have the CNO abundance in the hydrogen shell. So the plot on the left shows, again, two models, the internal abundance profiles of hydrogen and helium, and in this case, the combined abundances of carbon plus nitrogen plus oxygen. And in this case, they have almost identical profiles everywhere, except for a small region in the hydrogen shell where one of the models has been artificially just boosted in the CNO content. On the right-hand side, we see the consequences in the HR diagram. So the original model, which appears as a blue supergiant, and then the model with the artificially boosted CNO content just in that region of the hydrogen shell has a much larger radius and appears as a red supergiant. So this is one of the two key impacts that metallicity can have on the evolution of stars, the other, of course, being the well-known impact of the metal opacity in the envelope. And fifth, we have the hydrogen abundance in the envelope. So the plot on the left-hand side shows two models with otherwise identical hydrogen and helium profiles, except in the envelope where they have a different quantity of hydrogen and helium. So the plot on the right-hand side shows the location of each of these models in the HR diagram. And as expected, the model with a higher hydrogen content in the envelope has a larger radius and is redder, a result of the increased hydrogen opacity. So we built up a list of these, the six properties that set the effective temperature of massive stars. So I just discussed 5 of these. The 6th property is the metallicity in the envelope. And these properties are listed according to whether they favor a blue or a red star. And just very briefly to summarize them again, we have the core helium abundance, where a value of 0.5 favors a blue star, and a value closer to 0 or 1 favors a redder star or a slightly larger radius. The second property is the helium abundance in the hydrogen shell. The third property is the CNO abundance in the hydrogen shell. Fourth, a smaller amount of hydrogen in the envelope favors a bluer star due to the effects of opacity. Fifth, we have a smaller amount of metals in the envelope, also favors a bluer star. And finally, a core mass ratio close to 0 or 1 favors a blue star, whereas a core mass ratio close to 0.6 favors a redder star, due to the competing effects that we discussed earlier. So this kind of approach can help to provide a way to interpret observations of post-main sequence massive stars directly in terms of their internal structural properties, without having to also take into account the evolutionary history. So just going back to one of the original motivations for modeling stars and looking at stars in this way, we can now attach causes and effects in the evolution in the HO diagram. Again, some of these are well known, but some of them are much less clear just looking at an evolutionary model. For instance, this evolution down and up in the HO diagram can be attributed to a decrease in the helium abundance in the shell, followed by a subsequent decrease in the central helium abundance. And we can also apply this to the model at SMC metallicity and understand now why it follows a different kind of evolution. So here we have at the beginning of helium burning, first the evolution is dominated by the decrease in the helium abundance in the shell. We then have a contribution related to the core mass ratio of the star. And finally, the decrease in the central helium abundance causes the star to expand later towards the end of helium burning. So we can also test some of our predictions in a slightly different way. So this figure shows the results of a numerical experiment to investigate the impact of the CNO abundance on the expansion across the HR diagram after the mate sequence. So the black line here represents the normal evolution during the mate sequence of a 16 solar mass star at SMC metallicity. The black point represents the point of core hydrogen depletion, and the subsequent evolution along this black line towards the green point is the standard output from the evolutionary model until the beginning of core helium burning. So as a numerical experiment, we took the model at this black point and artificially boosted the CNO content of the hydrogen burning shell in the same way that I plotted earlier. And we then let the star evolve to the beginning of core helium burning. And we see it follows this red track all the way across the HR diagram to become what would appear as a red supergiant. So we see that this test is representative of the fact that the structure properties that we discuss for the post-main sequence also impact the evolution across the HR diagram at the end of the main sequence between hydrogen depletion and the onset of core helium burning. So the models and numerical experiments that I presented so far are mainly interesting from a theoretical point of view. So I'd like to now discuss some of the consequences of these models for observations, touching on red supergiants and strip stars. So most massive stars will end their evolution as red supergiants. They're the most common progenitors of core collapse supernovae. And supernova progenitors are particularly useful to study because we know their evolutionary stage, that is, that they are at the end of their life. Whereas for all those stars, we have to rely on the models to determine their evolutionary stage. And one of the exciting advancements in the last 2 decades is the direct imaging of core collapse supernova progenitors in pre-explosion archival images. So the analysis of these observations in combination with other techniques such as supernova light curve modeling can help us make connections between core collapse supernovae and their progenitor stars, and to improve our understanding of the complexities and uncertainties in the evolution of massive stars. In this project, we use the snapshot models to investigate what we can tell about these kinds of observations of stars at the pre-supernova stage. So a star with a given final helium core mass can have a range of final envelope masses depending on the evolutionary history, including binary interaction. For instance, you can have a helium core with no hydrogen envelope if it's been fully stripped off, with a small amount of hydrogen if it's been partially stripped, or with larger hydrogen envelopes, perhaps through a merger or in the context of a mass gainer. And so to study the range of these possible supernova progenitor structures, we built grids of static models with different core masses and envelope masses. at the pre-supernova stage. So let's first look at the location of a series of snapshot models at the pre-supernova stage. So plotted in the HR diagram on the left, the series of models here have the same core mass, the same helium core mass of 4.3 solar masses, corresponding approximately to a 14 solar mass star if it was a single star evolution. And envelope masses here ranging from 0 on the left or to 25 solar masses on the right. In the right-hand panel, the total mass is plotted as a function of the effective temperature. So the first thing to note here is that as the envelope mass increases, the luminosity remains approximately constant. And this is because for stars at this stage, all the luminosity comes from the helium core. And they all have the same core mass, so they all have the same luminosity. And the second thing to note is that over a very wide range of masses here from about 5 to 30 solar masses, the luminosity and effective temperature vary very little. And this variation is much smaller than the observational uncertainty. And this demonstrates that by using luminosity and temperature alone, any individual determination of the final mass of a red supergiant is going to be degenerate. So we repeat the same exercise for a range of different core masses and find the same result. So this range plotted here covers the vast majority of core collapse supernova progenitors. And the advantage of systematically constructing snapshot models in this way is that we can accurately map from a given region of the HR diagram to a range of allowed core and envelope masses based purely on the stellar structure, and also to quantify the degeneracies that exist. And then we can compare them to these archival images of supernova progenitors. So based on this grid of models, we produced a relationship between the final luminosity of a red supergiant or a strip star and its final helium core mass. That is independent of the typical uncertainties in an evolutionary model. And by fitting this, we produce this equation which can map from a given observed luminosity to the final helium core mass. So I'd like to briefly move on to strip stars now. So a large number of strip stars are actually expected to form in binary systems. And using the snapshot approach, we computed a grid of static stellar models of strip stars during the middle of core helium burning with a range of core masses and envelope masses. In this regime, the luminosity depends primarily on the helium core mass, and the effective temperature depends primarily on the envelope mass. So the plots shown here show the envelope mass on the left-hand side as a function of luminosity and effective temperature. And on the right-hand side, the core mass is a function of luminosity and effective temperature. And by computing a grid of these static models and interpolating between the models, it's possible to determine the allowed values of the core mass and the envelope mass for a given luminosity and effective temperature. So knowledge of these core and envelope masses can help provide constraints on the physics of Russell overflow in binary models. And we can also use this grid, so for instance, to compare it to the observations, in this case, comparing to HD 45166 as an example. And the values we obtain through this method are consistent with what's been found with detailed binary models. So just to conclude the presentation, we discussed this modeling approach we call snapshot, consisting of static stellar structure models that can help to isolate the connections between the stellar interior and the observable surface properties. We applied this method to investigate cause and effect and the properties that set the luminosity and effective temperature of massive stars during the helium burning. And we also applied it just to study masses of red supergiants at the pre-supernova stage and of strip stars during core helium burning. So thanks very much for your attention.
Thank you very much, Eoin. Very illustrative experiments. I think this is a talk that I will recommend to my future students, because it's very nice how you can learn with this approach you have explained us. So time for questions. Please tell me in the chat, and then I will. Anyone here wanting to ask any question to Eoin? Matthias?
Yes, Eoin, can you maybe go back to page 15?
Sure.
Yeah, so my question is there about when you made the first change,
Yep.
it already looked like that the luminosities immediately change also below the region where you made the change. So I do understand why there's a peak and why changes are happening outside, but why is also the core changing?
This value, this
Yes.
L hydro value that's
Yes.
plotted. Yeah. This very quickly goes back to as in this region of the star, it very quickly goes back to a flat profile. I think this is a numerical issue. It's just related to the fact that you've suddenly quite dramatically changed the abundance profiles, and you're keeping the old stellar structure solution. And so it takes this is the first time step. So after like 3 time steps, it looks more, it's less peaked here. It looks more like a smooth profile that you might see in an evolutionary model.
Yes, it went away very quickly, but I was just thinking on where it came from originally.
Yeah. Just numerical. Yeah. Good question. Yeah.
Ken, maybe you want to ask yourself the question, if possible.
Sure. Yeah. I think this is a powerful technique. I mean, it's obviously right now limited to one-dimensional models. So I was wondering is there any way to speculate or think about how you could imagine doing something similar to understand gradients within each radial sphere, say chemical gradients due to rotation or something like that?
I'm not sure I understand the question.
Well, I just mean that, you've got a real nice device for you. So you change a chemical composition at radius X, and this happens to the star globally. But you could have gradients within each radius if you have something that breaks the 1D symmetry, like rotation.
Yeah.
So I was wondering is it possible to use this technique to imagine what happens if I change the polar composition over the equatorial composition and see what effect that would have on the star?
Yeah, I think it's absolutely possible. Yeah. In fact, I think not to the same extent, but I think people have experimented with this briefly in the past. I'm not sure of the exact paper at the moment, but yeah, I think this is possible. I think at least the effects with regard to rotation are reasonably small quantitatively compared to the effects of the actual chemical composition. But yeah, interesting.
Joe, please.
Okay, thanks a lot for this very nice talk. It was very interesting, and I congratulate on your approach. And now comes my question. I completely understand that you have used MESA in the old times when you were working not in Geneva. Have you now tried whether this approach can be also run with the Geneva models? The background of the question is that MESA will never, at least to their authors, include the advective angular momentum transport, and that would be interesting to see in the earlier phases when we still have a strong rotation, what happens then.
Yeah, certainly. I guess my understanding is that Georges Menet and André Médère have done some tests in this direction in terms of the hydrostatic effects of rotation quite some time ago. And so in that context, we decided that, and I think quantitatively the effects are quite small, and a lot of the evolutionary effects that you see are ultimately propagated through the changes in the chemical abundance profile, which is the thing that I'm able to parameterizing this method. So I think it's something that's worth looking at some point, but we haven't looked at it.
Yeah, that was not the core of my question. The simple core of my question is, would it be as easy, in quotation marks, as running these or setting up these snapshot models in Mesa? Is the same possible also with the Geneva code? Have you looked into this method, whether it would work?
I haven't personally done it, but I think it would be technically similar. I think it would be just as easy, yeah.
Okay, good, thank you.
Yeah, thanks.
Fabrice?
Yes, so thanks for this very nice talk. I was wondering whether you could elaborate a little bit on the physical processes that would cause the changes you artificially include. Like, for instance, as we see here, a slight change in the profile of helium abundance. Is it mainly related to the convection properties, or is it, well, I guess you can have rotation or whatever, just the physical properties that would cause this?
Yeah, yeah, great. Mainly convection is what I'm imagining here. So there's kind of 3 ways that it changes that I think that I can think of that are changing, like in this example that's shown here. One is if you implement convective overshooting during the main sequence in a different way, you end up not just by increasing the core mass, which actually can change the shape and the slope of the hydrogen and ultimately the helium profile, so that, and then that change can propagate forwards. You know, you can get these convective shells between core hydrogen burning and core helium burning that appear just above the hydrogen shell, and if they propagate low enough, they can produce various shapes. And also this depends a bit on this is not really convection, but it depends a bit on the evolution of the helium core mass coordinate outwards through that. So that's like at different stages during helium burning. As the core mass moves out, the shape in that shell changes as well. And then, of course, you mentioned rotation as well. It's this can also, but I'm thinking it's mainly convection for this example. Yeah.
Okay, thanks.
Yeah, thanks.
Jaime?
Hi, thank you for this very interesting talk. So I have a question regarding binary evolution and metallicity. But I have to admit that I was a little bit late for your talk, and I think I arrived just when you were talking about main sequence or consequences for the main sequence. And so if I understood correctly, at later phases of evolution, the impact that a lower metallicity can have on binary evolution is that binaries could essentially interact at later phases of their evolution. Is that correct?
I mean, I'm not sure I was just saying that exactly, but maybe perhaps you could go on with the rest of the question.
But so if you have a lower metallicity, you remain more compact through the evolution, right?
Yes, yeah.
So interaction when the star evolved, right, and increase its radius, it might happen at later phases, right?
Yeah.
But I'm wondering if this is also the case at the main sequence.
Yeah, I see. Yes, yes. So they're more compact. We see this in evolutionary models, right? Yeah. So, and it's the same to
Have you looked into the consequences for binary evolution in the main sequence? So, for example, could you estimate what fraction of interactions would you have at lower metallicity, let's say SMC metallicity, in comparison to the galaxy, for example?
I think no, and I think you would need to use binary evolutionary models to do this properly, to really have an idea of like the fraction and timing onset of interaction. I think this gives like qualitative hints and then some quantitative idea, but in terms of actually modeling computing the binary interaction, yeah, I think you would need the binary evolutionary codes.
Okay, thank you.
Yeah, thanks.
Any other question by the audience? If not, I'm going to take the opportunity to ask myself some questions. So I find very interesting this way to do the experiment. So I had some cases that I don't know if you have already explored or not. And in that case, either you have some idea of what happened or you have some intuition of what can happen. So the first thing is, obviously you are making changes that I assume are quite large to really see the impact. But in some cases, this is a bit exaggerated, no? So this is related to the first question: is how is this affecting? How is the, let's call, numerical noise affecting these things? How is the impact of numerical noise on the solution of the stellar evolution model? Is this something that can be tried and then probably you see that there's no impact? This is my first question.
Yeah, okay, I see. Yeah. So it's I'll just jump. I think something came to my mind. Okay. Yeah, so for you, we did some tests, quite a few tests, and in terms of the dependence of the solution that you get on the starting point. And this is mainly like a numerical thing because this is like well known for a long time that there should be really one solution in the vast majority of cases to the stellar structure equations. And indeed we find that, so whether we start really close or reasonably far away, as long as you converge to a solution, you end up at the same, the exact same value. Is that what you mean?
Yeah, so actually these effects are beyond what is limited by the computational effects. So you really, what you are showing, you really need big changes to make this other kind of path in the solutions. No?
Big changes in the abundance profiles, do you mean?
Yeah, for example. So I assume in all the numerical computation, depending on the precision you are taking in your computation, you're creating some numerical noise. So what is the impact of these effects on the final solution of the models?
It's reasonably little. I mean, you do see some numerical effects that you don't, that like, I guess, are a bit unphysical there. For instance, you can see in some cases, I mean, I think Matthias's question, for instance, highlighted one of them. You see that a little bit. You get some noise here with initially the first time step after plugging in the abundance profiles and then getting the code to solve for the structure. But ultimately, these numerical sort of noise or numerical issues are washed out because the code will converge towards a solution. And if it converges towards a solution, you're good to go. And then I think with regard to how small or big the changes are, yes, sometimes they're artificially big just to demonstrate the effect.
Yeah, that's
to make it nice.
Because then jumping to the real world is like also we have sometimes we assume when we compare with the observation, we assume, for example, a given chemical content, chemical pattern, but we know that stars do not have exactly the same initial abundances. So this is something that obviously you can explore, but maybe the changes are small in comparison, are not really doing these big effects, no? Or when you will consider that the changes in the chemical pattern will really affect these kind of things.
In the initial abundances?
Yeah, for example.
Yeah, I think so in some cases it can have like a reasonably large effect, and in other cases it's dominated by other structural effects. So it's one example. If you find yourself in a position, we see this with the sensitivity of blue loops. Sometimes the stars make blue loops and sometimes they don't. If you find yourself close to that sort of bistability of becoming blue or red, then small changes can have these large effects, and that's kind of the point of that numerical experiment that I went through. And in other cases, you're just dominated by adding a small amount of extra helium at the beginning versus not. Might have very little effect overall. It might just boost luminosity by some very small percentage, and the rest of the evolution is roughly unchanged.
Okay, so to explain my question is because when comparing with the observation, at some point we need large statistics to begin to see all these effects, to constrain better all these effects. And the only way to increase the number of stars is to go, for example, in the galaxy, to go to larger distances. So at some point we are going to begin to see different initial metallicities and blah, blah, blah. So
Yeah.
I think it would be interesting to see what is the impact of these not so large effects, changing in abundances, to then when we are comparing the models with the observation, to see, be careful to mix this population of stars with different metallicities, because then there are important effects that can be producing one or other solution in the models in the way you are showing, no? But maybe these changes in metallicity within the galaxy are not so, the impact is not so large, and then we are in the safe side, no? But at least your tool is a way to do tests in this direction. This was my question.
Yeah. Okay. Yeah. I think the answer is that it will often have only a small effect, but it might have a large effect. I think you also need to look at evolutionary models to get a good answer on this.
Okay. Matthias, you want to answer?
Yeah, I would have another quick question. So as we are just at this plot, they changed the core abundances. So why is also the position of the strong increase, so the core boundary, changing? And did you try to make that align to keep them at the same mass coordinate or radius coordinate, depending on?
Yeah, so this is because I'm allowing the model to mix by convection if it wants to, in the sense that it's like at equilibrium with respect to convection. So if you put an input, for instance, you take the middle model at 0.52 and you sort of draw the abundance profile to go straight down and across, the convective core mass that the star wants to have is larger than the region of the flat abundance profile, so it'll actually just mix out by itself. And so you get, this is like a reflective of evolutionary models, so it's actually a good in this context to have that. It's a bit more realistic.
Okay, and maybe we can have the last question by Ken again. You want to ask yourself?
Yeah, I was also curious about those regions that don't allow a thermally relaxed solution. If you think there's any physical interest there, like a Hertzsprung gap kind of situation going on there.
Yeah, I think so what is ultimately happening is you have this kind of on-off nature of convection in the envelope. So you have obviously the red supergiant, you either have this large convective region or you have a blue supergiant with potentially a lower convective zone, but obviously no convective envelope. This should cause a gap. The Hertzsprung gap, I guess, is I think historically been sort of supposed to be a bit wider than that all the way across to higher temperatures. But I think we should expect to see a lack of stars there by number.
Okay, so I think today this seminar has been a real success because of the participation, because of your great talk, Eoin, and because of all the questions we had the possibility to discuss. So I'm very happy, and I hope the next one will be similar. And let me then finish by thank you very much for accepting our invitation, Eoin, and hope to see you very soon.
Yeah, thanks very much for the invite.
And thanks everybody for joining and making this possible. That's all.